Greetings, everyone. Since we may have some people from around the world, my name is Marlon Gillette. I'm the IEEE Buffalo Section Chapter Chair for AP-MTT. You may be curious as to how I came upon this particular subject. I was engaged in looking around about 3 months ago for software related to microwave filter design. Might point out my background started in filters about year 1999, and everything was manual at that point in time. So now the technology has changed a lot, and so whereas I had to do a lot of manual calculations, now one can obtain software. And how I got onto SynMatrix was a computer internet search. And I came across, I was using the words coupling matrix synthesis and came up with SynMatrix. And so I contacted them, and that's how we got the speaker this evening, Diamond Lu. And he is one of the former co-founders in this organization. Let's see, dated 2018. And he has 13 years of design hands-on experience, as pointed out in his biographical information on our announcement flyer. So, Diamond, please proceed.
Okay, thank you. Thank you, Professor Marlin. Okay, good morning, good afternoon, and good evening, everyone. So welcome to this virtual seminar held by IEEE Buffalo session. So my name is Diamond, head of R&D in SynMatrix technology. And today I will give you the topics on this designing microwave filters using automatic 3D modeling and AI optimizations. So first of all, I would like to appreciate Professor Marlin, who is the chair of the Buffalo section, invitation on this event and help from the Judys. And I hope you guys will enjoy this event. Okay, so this is the agenda for these presentations. So first of all, it is a very brief introduction to SynMatrix technologies and myself. And then I will take you guys to have a journey to view each major functions of this software. So you will see its capabilities and how convenient to use on future designs. And after that, so a new advanced design workflow will be proposed, followed by two design cases. One is for coaxial cavity filters. Another one is for the waveguide filters. Okay, so let's buckle up and start the show. So about myself, be honestly, I'm the no-name engineer. But I'm with the full passion on the microwave engineering. And right now I'm trying to make the engineer life simpler and better. As a microwave engineer, I have the personal struggled with using a lot of tools to design, optimization, and test and tuning. So my dream was to create the one tool that can seamlessly transfer every information easily between each of the design phase. So this is also my motivation to found these companies. And I can imagine there will be a day once the design specifications are given and simply click the buttons, you will have your designs. So now I'm on the way to achieve these goals. Okay. Oh, okay. So about SynMatrix Technologies. So SynMatrix Technology Inc. is a software technology company in Toronto, Canada, and it was founded back in the 2018. So our focus is the RF passive component design, simulation, test, and measurement work. And the first step is focusing on the microwave filters. So we have been Ansys solution partner since 2020 and have built automatic workflows directly into the HFSS. So some of which will be presented today, like the 3D automatic modelings and AI optimizers. So we also build this test and management workflow to help engineers and technicians tune these filters in the real time. Okay, so this is us. About this software, so SynMatrix, it can cover a wide range of applications. So for examples, it can cover from the VHF into the millimeter wave applications and covering the structure like the metallic cavities, ceramic cavities, and also the planar, coplanar, waveguide, and some LTCC applications. So it's all these coupled resonator-based topologies and structures. And within these years, we will provide non-coupled filter design solutions, which can cover more applications. All right, so as I mentioned, this is a software can provide the complete then-to-then design experiences. So the first step is the specification analysis. A bunch of the comprehensive functions will allow engineer to analyze the RF performance thoughtfully. And then they will analyze the RF performance, transfer this RF performance into the 3D structures automatically, and run this AI optimizer in HFSS. So after that one, the prototype may be diagnosed by using our real-time test and tuning tools. And the final stage for these mass productions are supported as well. So it can improve the working efficiency and enhance their product qualities. All right, so let's start this journey on each sections. So first of all, it's a specification analysis. So for this function, it's all about the filter synthesis and overall RF performance evaluations. So we can support varieties of filter synthesis like this bandpass filter, bandstop filter, low-pass filter, and multi-band, including dual band and triple band. So we can offering upgrade topology setup with user-defined the transmission zero positions. And for this bandpass filter and bandstop filter and multi-band filter, we can provide corresponding computer-aided tuning capabilities. So for low-pass filters, SynMatrix can support full practical step impedance the coaxial structures. So the round cavities and square cavities with a dielectric spacer or sleeves. We also can offer direct dimension synthesis and automatic modelings in HFSS, turning these hours work to minutes. So here, this is a very short videos to show this process. Played it. Okay. So this is our GUIs. So there are 4 options. So low pass is one of them. And go there, user can define the filter orders and cutoff frequencies, and also the return loss. And there are lots of geometry they can select, like the chipset filter or max flat. Then first step, we will synthesize the LC-based circuit. And once the user select the geometries, we can convert this one into the physical dimensions there. Go to the simulations and click the simulation. Then we can build the model in HFSS automatically. And all these parameters we turn into the variables, so user can change it by themselves. So after this running, as you can see, this overall art performance is almost 90% similar as our evaluations performance. So usually it is the hours optimization work. So probably right now it just take the minutes, you can finish everything. Okay. So outside this two-port network, we still support this multi-port network like the duplexers or the triplexers. We can support arbitrary topology synthesis and also support like the T-junction or common resonator types synthesized work. And to overcome some deficiency of this synthesized work, we still have this generic matrix optimizer to allow user to optimize their coupling matrix in order to meet their design specifications. And except this coupling matrix synthesize, so SynMatrix provide a bunch of comprehensive functions to allow user to analyze their overall RF performance, such as stored energy curve to allow user to evaluate their peak power handling capabilities. And also user can, excuse me, input and output their SMP file and edit the matrix. And also user can evaluate their design specification by considering these thermal drift predictions. And also we provide multicolor analysis to allow you to analyze how sensitive of your coupling matrix. And also this optimizer will allow you to optimize the filter with very special topologies. And finally, it's about some dispersion effect simulators. So I probably will combine this information into the case studies. So you will show, I will show more details about this. All right, so the second stage is about 3D modelings and optimizations. So to be clear, this 3D modeling functions is under the beta phase. We will release this function in the February, which is the next month. So by carrying over this information from the last step, we assume the user already get the corresponding coupling matrix and finalize their IF performance evaluations. And then we will turn this electrical performance into the real 3D models. Okay, so first of all, every design just starting from some single piece. So this is about single cavity designs. So our 3D modelings will provide various the cavity resonators with different shapes, such as coaxial type, rectangular waveguides, and cylinder waveguide. And the frequency and unloaded Q will be provided with directly synthesized the cavity size. And the mode chart will be provided to the waveguide applications. It will be very convenient for the millimeter wave engineer to figure out the outband superiors. And additionally, for these coaxial type filters, the temperature drift analysis for partial structure will be provided. So all user selected resonators can be constructed automatically in HFSS. So there is a quick video showing at the back. So after this generic introductions, I will play these videos for you guys. Okay, move to the next one. So it's about the coupling schemes. So we can take the coaxial cavities as the examples. So SynMatrix can support 4 major coupling schemes and up to 42 different geometries. So user can define these key parameters to proceed the parametric studies. And so I will show these videos later. And I/O schemes, which is input and output structures, are followed. So 3 major coupling schemes up to 9 different geometries will be provided. So same as the coupling schemes through the SynMatrix, user can control the HFSS to proceed the parametric studies. Okay, until this step, I think users somehow finished all the evaluations for these basic models, like the frequency, the Q, and the coupling coefficient, and whether you can obtain the proper tuning range. Then the next step, so we will do some 43D modeling work. So this function can support automatic generations for these 3D modelings based on user-defined topologies. And also we can support generic modeling with different rotation angles. So, you know, in the practical design, probably not every filter just go the 90 degrees rotations or 45 or 60 degrees. So sometimes their layout is very special because there is a lot of limitations from the mechanical side. And then after you build up these 3D modelings, all the parameters can automatically pass into the optimizers to allow you to proceed this optimization work automatically. Okay, so here this is the example to build up these generic structures. Okay, as you can see, user can somehow drag these the resonators, okay, and just rotate the degrees as you want. This is more generic to use. And in the meantime, you still can add these transmission zero structures between these the 2 resonators. So once you click the export to HFSS, then it will try to build up the models for you. So usually, during the designs, my design work, I almost pay more than 40% time on this modeling work. So it is not so technical, but it's really time consuming. But when you have these functions, as you can see, within the 1 minute, you can have all your models ready. Okay, so next step is about the compute-aided tuning and the optimizations. SynMatrix can provide 4 advanced ways to guide the optimization work. The first one is a two-part tuning method. So this is based on the rational polynomial way to extract out the error coupling matrix directly from either the lossy or lossless S2P file. The second way is we call it time domain tuning. This is a very traditional way, but it's more generic to use for all kinds of resonance-based RF performance, such as the filter, the coupler, and even antenna. So S parameter usually can be directly converted into the time domain response. The third one we call multi-port tunings. So this is still the very popular and traditional way to do the coaxial type filter designs. So on each top of the resonators, user need to build up this lambda port, and once they get the SMP file, SynMatrix can extract out the frequency and the coupling information based on Y parameters from this lambda port. The last one is generic optimizers. So it is a circuit-based method. It's somehow you trying to build up the circuit in the ADS or microwave office and import your simulation or test the data and do the generic curve fittings. So this is a very quick examples by using our computer tuning tools to design these filters. The example is relatively simple, but just to show the functionality there. Okay, so this is duraband coaxial cavities and duraband cylinder waveguide and band stop and this ceramic waveguide. Okay, so except this manually optimization way, so our AI method, our AI optimizer will streaming this work. So the new release, the AI optimizer, is based on the supervised deep learning method. So it has a two-stage here. So first stage, it will collect the data, tag the data, and sort the data. And in stage 2, it will based on the data behavioral, and then software will select either the space mapping or the deep learning method to optimize the structures. I will show more details about this method. And also the space mapping method. So this is a very traditional but very popular way to optimize the structures. We integrate this method with the two pre-training method. So this is a fully train and this is a smart train. So for fully train, we will train each variables inside this coupling matrix and try to build up this derivative matrix, and it can use to speed up this optimization process. So for these smart trainings, so it will smartly sort these training groups and only train some key parameters with very sensitive properties. It is suitable for the traditional cascade triplet and cascade quadruplet structures. And of course, I know sometimes for very extreme complicated structures, so the automatic optimization way may be the best option. This is why we come up this optimized, the customized optimization way. So this methodology is very similar as the automatic running process. So it will allow the user to control this simulation software. So step by step. Okay, so user only need to import this HFSS design and click run. Then the software will control the HFSS to run the simulations, export these as parameters, and return your optimal dimension values. User just need to check if these dimensions is reasonable or not. We have two algorithms at this running process. One is using the aggressive space mapping. Another one is use a linear slope method. So once they think this value is good, and then click run, it will step into the next iterations. So this page just show the collaboration with Ansys HFSS. So through the SynMatrix software, so user can set up this analysis, and also user can directly import HFS file into our platform, and we can import all the physical dimensions and variables into this software. And also for this workflows, during these optimizations, so user can check their coupling variations, dimension variations, and also once finish this optimization work, user can easily pass back this optimal dimension to the HFSS. So it's quite convenient to use. Okay, so once you finish the optimization, the next step will step into the either the prototype, the diagnose, or the mass production test and tuning work. So SynMatrix now support Rodenschwarz and KeySet VNAs, and also allow user to control the VNAs with filter tuning assistance. Some key the functions like the fully control and easy setup, and we support Ethernet cable connection so far. And once users set up this IP address, then they can easily control the VNAs, such as set up this testing environment. Just in 1 second, they can set up everything. And also during the test and tuning work, user can set up the trees, delete trees, and add the trees and split the displaying windows, and also change these the trees informations like the magnitude in dB or the phase of SWR. And also once user set up these specifications and markers, all this information can sync up with the VNAs. So user doesn't need to touch the buttons in the VNA's instrument. And during this optimization, now the test and tuning, so we gave you the specific, the tuning instructions. On the head of the arrow bars, we will show in and out. So you just based on the in and out to either screw out or screw in. So this tuning is quite intuitive. About this tuning method, we have the two modes. One is for streaming mode, another one is for manual mode. Streaming mode used for relative mature product, used for the mass productions. Once you click started, and our software will constantly get the data from the VNAs and showing the tuning instructions. So for the manual mode, it's used for diagnose stage, and also most of the time used for planar coplanars. So think about once you have the macro straight plan, you want to cut and try, and once you cut and try, you need to click this button, we will update the result. And we have the two tuning method. One is based on the frequency domain, another one is based on the time domain. Okay, so for time domains, user can upload their S2P file as their the references curve, or we call it the golden curve. Okay, so so we will convert these S parameters directly into the time domain and do the references comparisons. All right, so this is how generate for this SynMatrix software introductions. I hope some features will create some resonance with you. And clearly, based on these previous introductions, so we can propose this advanced design workflow, create the golden matrix and step into the automatic 3D modelings, and then do the automatic optimizations, and then do the test and tuning work. This is the whole workflows and some details apart. I don't want to pay much time on this one because some of the parts are overlapped with my previous sections. So rather than that, I will put this workflow into the next case studies. So you will learn how it works. Okay, so the first one is the rectangular coaxial cavity filters. So here I can show you the first step, this specification analysis. And also step 1, so user need to input these design specifications like the return loss, oscillations, the insertion loss, group delay repos, and insertion loss repos, sort of this. And after that one, user need to define these filter information like the filter order, return loss, and frequency informations. I know, especially for these filter orders, it is like the experience-based numbers or values. So user may try or repeat many times until they can get the desired RF performance there. And also, if necessary, so user can add the transmission zeros into this the RF performance, so it can improve their outband rejection performance there. And then user try to define these topologies based on the mechanical request, and then click calculate all. They can get the corresponding golden matrix, and also the RF performance is there. Actually, during the real designs, probably user need to consider about more. So for example, some mechanical parameters like the temperature shift, the thermal drift. So user may do some, iterations on these RF performance optimizations. So we provide this shift. We call it fine tuning. User either can tune their center frequency or extend or narrow down their bandwidth to somehow gain the right design margins there. So after you get this golden matrix, then you can step into the 3D modeling work to build up these models. So we will start from the single cavities. So in this case, now we select this rectangular, the square one with the ball on the top structures. Okay, by given the proper the radius range and resonator height range, so we can quickly get the corresponding the frequency and the Q information here. Okay, the proper geometry can be obtained quickly, and based on this information, the 3D modeling work can be easily done in the next step. So there are more details about this one. So 3-step design workflows, the cavity designs, and then the tuning screw designs, and also the HFSS simulations. So in order to meet some designs, more practical designs, so you see the draft angles for the cavities and also the resonators, and also edge roundings functions are also added. So in the meantime, the temperature compensated partial structure are still supported. So user can select the proper materials for this housing and the top resonators and also the steels, and then we can retain you the optimal ratios. It will help on this compensation work. And then move to the next one, this coupling coefficient simulations by selecting the proper coupling schemes and set up the simulation analysis. So user can do some parameter studies to figure out if my average width or tuning screw depth can meet my tuning range. And finally, it's about input and output structures. So we can support 3 popular input and output coupling schemes like this, the tap couplings, disc couplings, and the loop couplings. And worth to mention is for all these modeling work, like the single cavities and also coupling schemes and input and output structures. So we all support parametric studies. So user can set up their interest key parameters and proceed these sweep simulations. Okay, so this is a short video to show these workflows. So starting to build these single cavities and then coupling schemes and then input couplings. Okay, I can play this one. So here, this is my selections. So this is to show the functionalities. This is some help files to help you to the rounding edge. And then I set up the simulations, then try to build up the models in the HFSS. Okay, so this is a single tap, as you can see, very easy to build up. And then you can select I select the tuning screw on the top as my parametric studies target. Just a sweep 3-point. So once the simulation is done, it can return my relative, the frequencies and the Q values there. And then step into this coupling schemes. So I select through windows, the coupling structure there. And I don't need to set up everything, just click next. Then it will give me the proper structures there. Okay, what I need to do just figure out how deep of these tuning screws in the middle, or maybe the width of the areas, to make sure if this dimension is within my range, my tuning range. So that means that this the coupling coefficient coming from the HFSS need to meet my design coupling matrix goal. Okay, it's pretty quick to finish this one. And then I will do the input structures and study there. So same as before. So this result will be reflect as group delay to to detect whether I can get the proper input and output coupling there. Okay, so the next video is about the total layout there. So as you can see, though, this is square windows, and then I can just rotate, right? And then I just build up these transmission zeros, and then click started. Okay, so maybe 30 seconds, you have everything ready. Next step, what you need to do is just transfer this modeling into your optimizers. Okay. All right, so in this optimization stage, so we provide two workflows. So first workflow is through this perturbation system, and then put this derivative matrix into either AI or space mapping. The second workflow is just go through this, go to the AI or space mapping directly. So for this case, we use a workflow 2. Comparing with these two workflow, the difference is for first one, it can be used for some simple and medium levels design case, such as chip-chip inline types of filters, and also the filter order is lower than 8 with less than 4 transmission zeros. The most important thing is this coupling matrix need to be insensitive. The second one, workflow, can be used more generic. Say, I don't know how sensitive are my coupling matrix or my structures, and I don't want to waste the time on these perturbation runnings. Then just go directly to the AIs. So it can handle the filter order higher than 10, and also with the transmission zero than 4, with these very complicated case designs. The reason why I go to the AI workflow tool is through this multi-color analysis, I run 5% changes on this one. So as you can see here, this is the self-couplings, which is the main coupling, and the sequential couplings, and the whole matrix. So when I do this multi-color analysis for these sequential couplings, apparently, as you can see here, the transmission zeros changing too much. So my target is just to design 3 transmission zeros, but sometimes it just show 1 or show nothing there. Okay, and also when I do the whole matrix sensitivity analysis, you see the return loss degrade too much. So that's why I just go through the second workflow. I don't want to use the perturbation system. This is the initial response after this 3D modeling work. And when I put into the AI optimizers, so this is the running process, initial 10, 27, and until the last one, I can get very decent result there. So, okay, so this is the running process histories. So as you can see, the global arrow was dropping constantly, although there are some spikes, as you can see here. This may caused by either the simulation errors or the matrix extraction errors. As I mentioned in the before in the Monte Carlo analysis, the sequential coupling is more sensitive than the self couplings. So the algorithm will specially treat these the sequential couplings, maybe give this more runnings, and also you can see the minimum errors is done can be the initial one is a 3.7 and can be down to the 0.032. Okay. Okay, so second one is the waveguide case used for the high frequencies. Of course, the first step is the same as the previous one, so I don't need to pay too much effort on this one. But there is only one parameters need to be mentioned. This is a dispersion effect controls. So this function is trying to emulate the RF performance with a different phase velocity versus the frequencies. Actually, this is a distortion. So you may have the appearances that distortion when you're trying to design the filters like the one-band applications or planar, coplanar structures or ceramic or waveguide. Sometimes you will see the higher side just the rising up or lower side sitting down, or the both side rising up or sitting down. Okay, so it might be because of the near-band spurious or the phase distortions. So this function will allow user to estimate this effect and predict whether you can pass your specification or not. Because for ideal curves, it almost have the symmetrical slope for the lower side and the higher side. But in realities, most of the time you will see there will be one side just rising up and sitting down. So we call it a skirt effect as well. So, and also the reason why I use this one is because in the real design models, as you can see here, in the middle part, I use the TE102 mode in order to create 90 degrees phase differences to generate the transmission zero at the lower side. And here, this is some mapping rules between the optimizers and my coupling matrix. Okay, so when I optimize the resonance frequencies, I just tune this waveguide length. And also when I optimize the couplings, I will optimize this the Aries width. And in this work, I just go through this perturbation system because I still did Monte Carlo analysis with 5%, and I eventually found, firstly, this transmission zero position has minimal impactions. Secondly, I see this return loss degradings is not so serious comparing with the CTCQ hybrid structures. So actually, the most difficult work to this optimization is the transmission zero position. As you see, there are 3 transmission zeros there. So they must match with the topology settings. And during these optimizations, so these positions might be matched up with each other. So the algorithm need to get sort of them correctly. Otherwise, it will crush the whole models. And secondly, some spurious may come from this TE102 mode, and it might impact this coupling matrix extractions. So the dispersive effect control need to be considered. Okay, same as before, this is the initial response and frequency, and the couplings it detune a lot, especially for frequencies is off a lot from this the error bars indications. Okay, so the first step, we will running the perturbation system to build up this derivative matrix. A small amount changes to each tuning variables, such as the length of the waveguide and the width of these arrays, so will be made. And we can assume that the actual electromagnetic fields inside this cavity are not greatly different from the unperturbated models. So there is an example, I perturbate the M44 here, As you can see, only the M44 arrow bars has a minimal change here. But you know, the case is not so ideal. For these couplings, it might be impacted as well. Okay, so this is some perturbation function there. So our system can perturbate each variables together in automatic ways. So we can support the symmetric and asymmetric perturbation process. So if you have the chipset filters or maybe the filter with symmetric notch levels, you can use the symmetric way to perturbate it. It can save your time. And secondly, we can automatically return these recommended perturbating values. Say, I don't have any concept of this perturbation dimension there. I don't know how much do I need to perturbate. Then don't worry, we can recommend the proper values to you. And you know, since these variables just have a very small amount change, we will monitor the HFS simulation process to provide you if that simulation is convergent or not. So as you can see here, there's a red dot that means your simulation is not convergent, because not convergent may not be able to give you the correct answers or accurate simulation result. It may impact your deviated matrix accuracy there. And also, if you found this way, of course, we allow user to reperturbate each individual variables. They can manually control it. So before going through this optimization result, so please allow me to take 1 to 2 minutes to introduce our AI core network principles. So we have the 4 major functions. The first one is smart grouping functions. So we will, based on the perturbation system or pre-training result, the algorithm will sort out the data and create optimization strategies. By smartly grouping these different frequencies and the coupling element, the impaction to each other can be avoided. So the grouping work may ensure this stable optimization process. So second way is we call it a deep learning system. So the slope information to each variables inside this coupling matrix will be collected and also will be proceed with the curve fitting method in further to return you optimal result. And during this process, the adjacent couplings impactions between each variables will be considered. The third one is stabilize the control system. So this is try to avoid a nonlinear effect coming from the curve fitting system. Say sometimes due to this nonlinear effect, so the curve just increasing or decreasing exponentially. It may return you some ridiculous dimensions, and also this dimension may crush your models. So once these things happened, it will trigger our parameter variation control system. So to ensure this stable optimization process. The last one is we call the smart convergence system. So we do expect every parameter changing. I mean the coupling coefficient versus this dimension changes can be the linear. The smart convergence system is based on the arrow changing histories to narrow down these trust regions. We call it the trust regions because we can assume that with the very small changing, small range changing, the dimension changing versus the coupling matrix errors will be linear increase or decreasing. Okay. Okay, so this is the final result there. So as you can see, same as the previous one, this is the arrow curve just dropping constantly. And also the arrows can be from the 6.13 down to the 0.025. And for both written loss and the rejections, we all can meet the specifications. This is the plot of the running process. So initial and fourth, 10th until the last one. And once we return back all the geometries to the HFSS, then I can get the similar result. So, okay, so here, this is some summary for this optimization. So optimization is always headache to most of engineers I know. So I want just to share what we have observed to this work. So first of all, it is a study to this relationship between the coupling coefficient and the dimension changes. So most of the time, we do expect to see the curve is close to linearly increasing or decreasing like this. Okay, so it is true for most of the some simple designs like inline type chipset filters with limited resonators, maybe and some maybe simpler topologies. The coupling matrix is very insensitive, which means each physical variables changing is relative, independent. And for this case, designs, no matter for space mapping or AI, the both of method can get convergent result quickly. So, however, the life is not so perfect. So most of the time that you will see the curve is like this one, and also like this ones. Okay, so there are some reasons to cause these issues. So like the number two, it may be some most of the time it happened for these transmission zeros. That because sometimes if your tuning structure is very close to the resonating structures, it may cause the very high energies, either the electrical or magnetic, around these structures. So it may cause some nonlinear property changes. And also for these ones, so from what we saw during the simulation, they said because the layout, say the two cavities is really far. When you sweep the arrays or do some the tuning screw insertion, it won't get reach to that such couplings. And for the last ones, it may happen to the simulation errors or matrix extraction errors and cause this vibrating result there. So you don't need to check them and find out the root cause and then proceed the optimizations. Otherwise, it just wastes your time. And also for our optimization process, then it can be divided into these three zones, say the sensitivity zone and non-sensitivity zones and moderate sensitivity zone. So from the return loss is 2 dB until the 10 dB, we call it sensitivity zone. In this zone, the coupling changing versus the dimension variations is nonlinear due to this EM field interruptions or maybe some inappropriate parasitic coupling effect. This is in the initial stage. So under these situations, AI might be the best option to help you to obtain the initial response. And starting from this 10 dB to maybe 20 dB, we call it the non-sensitivity zone. This is like the honeymoon between the couplings and the physical dimensions. So they are changing linearly with each other. So with these zones, no matter for the space mapping or the AI, so it can get converted quickly. So when the return loss is get deeper, so you will see some, the vibrating effect again. So both of these coupling coefficient and physical variables will fight with each other again. Okay, so in that case, so we usually use just increase the accuracy, the simulation accuracy by adding the mesh to increase to improve these optimizations. And some key parameters to this success. So whether you can get accurate metric extractions. So say whether you set up these dispersion factors or whether you have the proper capture range or maybe the simulation point is enough or not. And also the second one is the EM simulations. You need to ensure you can get as much accuracy result from the EM simulations. And also, you may create the appropriate strategy for these optimizations in order to get these optimal results in the limited time. So for example, in the initial stage, your return loss is not so good. And at this stage, I don't think you will need a lot of mesh to run these simulations. It costs a lot of time and waste your resource on this one. So maybe at the initial stage, I just use a relative accurate result to do the optimization work. And when the return loss is down to the 20, then I can increase the mesh to increase the accuracy to get the converging quickly. So this is about the strategy simulations. Okay, so I know these two cases are not enough, to show these workflows or maybe hit your pain point. So in these years, we will create more application case, and user can follow us in the LinkedIn, Twitter, or the YouTube channels. If you would like to try on the SynMatrix, so please feel free to contact us through the support@synmatrix.com, and we are more than happy to help you on it. All right, so lots of things this might be some coincidence. So today is my little queen 6 years birthday, and happy birthday to her. And thanks for her patience on this one. So I will be with you soon. And in the meantime, so I would like to take this chance to wish everyone and your families and friends all best during this special time. I know it's hard. Please keep well and healthy. So I hope we can quickly fall into this world and back to the right track. Okay, so this is everything about these presentations.